Today we're going to talk about experimental probability. Yesterday we talked about theoretical. So our learning target is I understand the difference between theoretical and experimental probability. I can find the experimental probability of an event. You can estimate the probability of an event by using data or by conducting an experiment. And each repetition of an experiment is a trial. The sample space of an experiment is the set of all possible outcomes. Experimental probability, also referred to as empirical probability, is often used to estimate theoretical probability and to make predictions. Basically the same formula as yesterday. It's the number of times an event occurs out of the number of trials. So it's not a fixed number of trials like the things yesterday, like when you roll a dice, there's always only 6 outcomes. I can have more trials depending on the situation. So again, we're going to round our answer to the nearest thousandth, 3 decimal places. So example 1, the bar graph shows the results of 100 tosses of an oddly shaped number cube. Ones are 17, because I know it's kind of hard to tell on here, but there are 17 ones, 21 twos, 16 threes, 11 fours, 22 fives, and 13 sixes. Okay, so just in case you can't tell, because where exactly are they? So those numbers came from there. And these were from tosses. So someone actually tossed a number cube. So it's not going to be exactly 1/6. This is what happened. So assuming the die is fair, compute the theoretical probability of rolling a 6. Goodness gracious, I'm so sorry. Compute the theoretical probability of rolling a 3. So theoretical is what should happen. There was 1 out of 6 threes. From the bar graph, compute the experimental probability of rolling a 3. Well, from the bar graph, there are 16 out of 100 tosses. So theoretical is what should happen. Experimental is what did happen. Assuming the die is fair, compute the theoretical probability of rolling a perfect square. So again, theoretical is what should happen. On a number cube, perfect squares are 1 and 4, because 1 times 1 is 1, 2 times 2 is 4. So those are the numbers that we're looking for. So that would be 2 out of 6, or 1/3. But what actually did happen is different, and that's considered the experimental probability. So if I look over here, there were 17 ones, there were 11 fours, which is 28 out of 100, or 0.28. So assuming that the die is fair, choose the statement below that is true. As the number of trials increase, we expect the experimental and theoretical probabilities to become closer, though they may not be equal. The experimental and theoretical probabilities must always be equal. As the number of trials increases, we expect the experimental and theoretical probabilities to become further apart. Well, we've already shown that that doesn't make sense. They're not always equal. They should get closer together. When we did the M&M activity, we talked about the law of large numbers. The more times we roll, or the more times we do an experiment, it should get closer and closer and closer to the experimental. So take a second, do the try it. Assuming the die is fair, compute the theoretical probability of rolling a number less than 3. From the bar graph, compute the experimental probability of rolling a number less than 3. I'll pause the video or stop so that you can answer the question, and then you'll come back and we'll see if you got it correct. So a number less than 3, that means a 1 or a 2. So there are 2 out of 6 chances, or 1/3. From the bar graph, 17 plus 21 out of 100 which is 38 out of 100 for 0.38. All right, as promised, it was short and sweet. You now have an experimental probability practice in ALEKS. Make sure you check your times, log into your other assignment or other class after this. If you have questions, let me know. I'll be around all day. I'll see you tomorrow, hopefully.